Okay. Good morning. So today we are in unit 11. Actually, there are only a few weeks left before we will do our final presentation. Because we actually pull forward our final presentation to December the 21st, right? And that is actually a Sunday morning, right? Okay, so we don't have too much time left. And today we're going to, for the past 2 weeks, we learned two types of regression, right? The linear regression is used to predict the numeric target variable, right? For example, we can predict the amount that, for each customer, we can predict the amount that he will buy if he come to our store, right? The amount that he will buy is actually a numeric variable. It could be like 100, 200, like 1,000, 2,000, right? Okay, and that, in order to predict that numeric target variable, we are using linear regression, okay? And last week we talked about logistic regression. It also used the predicting variable to predict the targeting variable, but this time the targeting variable is a binary variable, right? It's kind of like a true, false, 0, 1 type of variable. So in the context of Tafang, we will use this model to predict whether a customer would come to buy in the next month, okay, right? So the outcome is only like 1 or 0, right? He would either buy or no buy, right? So when the target variable is kind of this binary 0 and 1 type of variable, we are using logistic regression, and we already say that in last week, right? The model is not predicting the y variable itself, okay? It is predicting the probability that y equal to 1, right? Okay? So that's the difference between these two models. And in the context of Tafang, we are going to in the context of Tafang, we are going to use these two variables to predict the purchasing probability, right? And also predict the expected revenue, right? Okay, and from that we can calculate the value that this customer will bring to the company, okay? But before we go to that, because there are some complications, right? So today we'll use a simplified example to run through the entire prediction, assumption, and simulation, so that you can have a better idea, have a holistic idea about how to do the analytics in kind of like a holistic view, okay? So yeah, see, because our purpose is actually to choose instrument, right? And to choose the target audience, choose the target customer that we want to marketing on. And also we want to evaluate the cost effectiveness when we are applying this marketing instrument to this group of people, okay? So, but that actually pretty complicated, okay? So before we go to the complicated case, today I'm using a simplified example, which is the example that we are using last week, right? Still remember the predicting medication, predictive medication case that we are talking about. there's an insurance company, right? So that insurance company is actually using the hospital data to predict the policy owners, the diabetes patients' probability of being poor care, right? Because if a policy owner, if a diabetic patient, they are like not they are not care well, they do not have a good care, they could have a lot of complication, and the cost of health insurance will be very high, right? So there's a very strong intention that the insurance company want to predict want to estimate or predict the probability for each of this diabetic policy owner. They want to predict their probability of being poor care, right? And then we are using logistic regression to do that, right? Because it is either good care or poor care, right? Isn't it? So today we are using this example because it's easier, right? It's only use one model, and the business scenario is actually simpler than the Tafang. So we go through the entire data modeling, prediction, assumption, simulation, and then use them to choose the instrument, to choose the target subjects that we want to apply the instrument, and also evaluate the cost effectiveness of each of this instrument, right? Okay. So today it'll be simple, and starting next week I would jump back to Tafang and teach you how to do the same thing in the context of Tafang. Okay. And in the final report, in the final presentation, actually it will be the same. The format of the final presentation will be the same as in the midterm, right? We were kind of like a contest, right? Okay. Yes.
How about the data set? We will use the same data set as...
Yes, we are using the same data set, but this time we are not doing data exploration. Okay, we are using the data to build model, use the model to do prediction, and also we will make some assumption and do simulation, so that in the midterm we only have a strategy, right? We are saying that we want to promote this group of customer. We want to focus on this group of customer, and we want to improve their purchase probability, and also improve their amount of buy, right? Like how many %, right? We just set the target, right? But the target would not fulfill themselves, right? We set the strategy, set the focus, we set the target, but the target will not realized if we do not take some marketing effort, right? Okay. For example, you need, in order to pull up the buying probability and pull up the buying amount, you have to do some promotion, right? You have to do some advertisement, maybe some coupon type of some event, right? And that type of event will cost money, right? So you need to choose the instrument carefully, right? And after you choose the instrument, you need to choose the target, right? And then you need to evaluate. When I apply this marketing instrument to this group of customer, what is the cost effectiveness? And in order to do that, we need to do prediction, assumption, and simulation, right? And before we go to the Dafang case, as I told you, I would like to use this predictive medication case to give you a simpler, a holistic idea about how to prediction assumption simulation will work together. Okay, because the predictive medication cases are rather simple. Okay, now let's have a quick review of the case, right? So you get you back to the context, right? So this case is like we are doing quality care of diabetic patients, right? As I mentioned, right? Okay, so we have a sample data. The sample data is that they actually have like 100 and 200 diabetic patients that they sample from all of their policy owners, right? Okay, so they may have like 1 million, 2 million of diabetics patient in their policy owner in the United States, right? But they cannot, when they do the model, they actually do not know the poor care or good care status of each of these patients, right? Okay, they only have the medical records, right? So they hire some expert to label this data, right? The expert will look into the medical records and label each of these sampled diabetic patients' data to and determine whether they are 0 or 1, right? So so we have data, and we hire some expert to like. So we have the data, do the sampling, have the data, and then we have the expert to do the label, right? Now we have X and Y, right? So we can build model, okay? Now after we build this model, we actually put the entire population, put all of the like 1 million. The sample is only like 200 points, right? So I can make a sample, but after I have this sample, I can actually use the sample to predict the 2 million, the entire population of diabetic patients. To predict what? To predict their probability of being poor care, right? Isn't it? Right? That is basically what we discussed last week. Okay. So we are back to the context, okay? So as I focus many times, you need to come in earlier. Otherwise, if you miss the opening context, then later on you may have trouble in to understand what we are doing, right? Okay. Okay, so. Maybe let's take a look at the notebook first to give you a better idea of what we are doing, right? Okay, so today we have two files again in our Google Drive folders, okay? So you get this zip file and put it into your code, directory, unzip the file, and you will see a directory called 11 underscore decision, okay? Get it? Okay. So go to this directory. Again, we need to like set this directory as the working directory. Okay? Everyone is here, right? Okay? Now we can open the first notebook, okay? It's event A, and then also we can open it in the web browser. So we are talking about the distribution of predicted probability, and we are talking about the the confusion metric. The idea, still remember that, right? The idea about confusion metric and also the accuracy metrics. Do you still remember that? Okay. So let's do it step by step. Okay. Let's do it step by step. Actually, the confusion metric and all of these accuracy metrics, they are actually derived from the predicted probability, right? Okay. So before we can estimate the accuracy of the model, we need to know the prediction probability, exactly the distribution of predicted probability. Okay. Now, so let's take a first look at this code chart. This is actually we already have done in last week. Okay. So maybe let's go into and again, first thing is you want to execute the first chunk, and then you execute the second chunk. Now in this second code chunk, we basically just read in the data, right? And we split the data into training and testing, right? Okay, we already explained why we want to do that, right? Because in modern data science, when we are testing the accuracy of a model, we don't want to test it with the training data, okay? So we basically, when we get the data, we split the data into training and testing data, okay? And when we build a model, we only use the training data, and the testing data is reserved to measure the model accuracy, isn't it? Okay. Okay. So now so this is the data set, right? The original data set, and we split it into training and testing. Okay. Now, and in each of this data frame, the columns are all the same, right? The first one is the member ID and the inpatient days, the ER visit, office visit. It's kind of like the medical record for each of the patient. Okay, so the data set, actually every row is the medical record of a diabetic patient. Okay, and the column, of course, is the detailed record of number of days, like it's inpatient, number of days visit ER, that type of things. Okay. Now, so with all of this variable, what we care is here, right? What we are interested in is whether this patient is good care or poor care, right? So this target variable, they only have two variables, right? As I already explained, this label are actually given by the diabetic experts, right? Because they are experts, so when they're looking into this medical record, they can actually determine whether a customer is good care or poor care. When they are, for those who are poor care, they will label it as 1, right? And when they are good care, they will be labeled as 0. Okay, right? So this is, and when we build a model, actually it's very easy, right? You just as we are building the linear regression model, we put the predicting variable, the target variable in the left-hand side of tilde, and in the right-hand side we simply put in all of the x, all of the predicting variables. Okay, and for simplicity, I only put two variables here, right? And actually, you can actually put all of this variable into this predictive model, and it will make the accuracy better. Okay, I just do this for simplicity, for demonstration purpose. Okay, and of course, you need to give it the data, the name of the data frame, and so you can see that I'm using the training data set, right? Which is only 75% out of the entire data set. And for logistic regression, to build model, you need to call GLM function with this argument, family equal to binomial. You need to do that, okay? Because GLM can build a family of models. Logistic regression is just one of them, okay? So you need to specify that this time I want to build binomial logistic model, okay? And as I say, the building model is actually a very easy job, right? Just make a function call and then you will get the model. The model name is, you can choose the model name, whatever you want, right? And then after you build the model, you can use this summary function to see the detail of the, to see the estimation of the coefficient, right? Okay, and then we can start to evaluate the model accuracy, right? Okay. Now, let's we already mentioned that before we can before we can evaluate the model accuracy, we need to do the prediction first, right? Okay, and again, do prediction is just from one function call. Okay, okay. So for now, I'm calling predict with GRM, which is the model, and then for probability, I need to specify type equal to response. Okay, so I do not give the new data, so this prediction would actually return the predicting probability. Okay, when I execute this, I will have a predict vector, right? And the length of the vector is exactly the number of rows in the training data, right? Because I'm not giving the new data, so right now it's predicting the probability of poor care. Okay, this is the probability of poor care for each of the 99 members in the training data set. Okay, so predict is actually just one line of code, right? And because there are a lot of numbers, right? If we see the vector directory, you'll see a lot of numbers, right? It's very difficult to have an idea of how the predicted probability is distributed, right? So in order to see the distribution, we can use the histogram, okay? So now this is I make a histogram, and I also make a red line at 0.5, right? Okay? For each one of these 99 observation, for each one of these 99 patients, we actually have their probability of poor care, right? So because it's probability, the value of probability is always between the range of 0 and 1. isn't it? Right? So for each of this point, they have a predictive probability, and this is the distribution of the predictive probability for training data, right? Okay. And when we have this predictive probability, then we will have the idea about confusing metrics, right? Okay. So as you can see here, now we can, for all of the patients that have the predictive probability higher than 0.5, we will predict them as poor care, right? And for those people whose predictive probability is lower than 0.5, we will predict them as good care, right? Okay, so that's the that's how we determine whether the predictive probability is higher or lower than predict. It's actually our prediction, isn't it? Right? And then the actual value is already in TR's poor care column, right? Okay, as we can see here, this is the poor care column within the TR. Well, I should actually take a look at TR. It's the same thing, right? Basically. So it's already here, right? So we have the actual value and we have the predictive value, then we can form the confusion metric. Still remember the idea of confusion metric, right? Okay. So let's take a look at this chart again. Take a look at these slides again. Okay. Actually, a confusion metric is a 2x2 metric. Okay. And this is the actual, and this is at the predicted things, right? And we determine whether, when the predicted probability is higher than 0.5, we say that it's positive. When it is lower than 0.5, we say it is negative, right? This is the predicted value that come out of the model. And this is the actual value, right? So now for this in these two dimensions, we can actually have 4 cells, right? Actually, you can say that any one of the data point would be classified into one of the 4 cases within the confusion metric. So, right? So that, if a patient his actual value is 0, right, and we predict them as 0, as negative, then we are predicting right. So we call it this case true negative, short like TN, right? Okay, and if it is actually 0 and we predict it's a positive, then this is the false positive, right? Because it's 0 and we predict it as 1, right? So this guy is false positive, okay? And then again, in the same thing, here is true positive and here is false negative, right? So any one of the point in the data set, they have an actual value, right, in the data in the data frame, and actually the model would give a predictive probability for each of this point, right? And when the predictive probability is higher than the threshold, we'll call it positive, otherwise negative. Okay, and so we have this 4. So every point in the data set would be classified into one of these cells. Okay, So the count of Tn, Fp, Tp, and Fn, they compose this confusion matrix, and the sum of all of this value is equal to the data point. Okay, it's always equal to the data point. And out of this four value, we can define a lot of different accuracy metrics, right? Okay, the first thing is accuracy. Okay, which is the number of the percentage of data point that we predicted right, which is Tn plus Tp, and the denominator is actually all the entire thing, right? And we also define sensibility, okay, and also define specificity, okay, and actually, there's a problem in calculating the accuracy of a model in this way, right? Because in the real business environment, we used to the threshold is not necessarily fixed at 0.5. Okay, sometimes we would like to raise the threshold, and when we do that, okay, when we do this, the number of positive, okay, would like drop down, right? Because actually, we are treating all of the, if we set the threshold here, right, then all of this point, they are treated as positive, isn't it? Okay, and if I raise the threshold and threshold is here, then only these 3 points are treated as positive, right? So as you can see that the distribution, I actually put two histograms here, right? The red color is actually y equal to 1, okay? The red color is y equal to 1. And this is the distribution of predicted probability for the patient that actually has poor care, okay? The red color histogram. And then the green color histogram is the predicted probability of the those member who is 0, okay? So when we take this example, if I put the threshold here, right, and I will only predict 3 points as positive, right, okay, but and 2 of them is actually positive, right? One of them we kind of like predicted wrong, right? So we have 1 point is wrong, okay? And as I pull up the threshold, okay, the this number would actually reduce, okay? And if I lower the ratio, this number will increase, right? Because we actually take all of the data points above the threshold as positive, right? Okay, so the lower the threshold, the more positive case there will be. So this confusion metric, it actually changed, right? It actually changed by threshold, and when the number inside the confusion metric change, all of this derivative accuracy metric also change. Okay, so here comes a problem that in the modern data science, basically when we measure the accuracy of a model, we don't like to use this traditional type of model, which the accuracy metric which will change with the threshold, right? So at the end of the last week, we introduced the concept of AUC, right? The area under curve. If you in today's folder, we will have one of this endsm.r, right? If you run this application. Open the browser, it's easier. Okay, so as you can see that this is the simulator, it's not the real data. I just want to simulate to give you an idea of when because this is the threshold, right? The purple color line is the threshold. So you have the confusion metric here. Okay, sorry, the word is actually too small, right? So all of this point, right? Basically the red point above the threshold are the true positive, right? Because they are y equal to 1, right? And they are above the threshold, so they are true positive. And for this green point that above the threshold, they are false positive, right? Because they will be predicted as positive, but they are not. Actually, they are not positive, right? Okay. So and with that, we can calculate the confusion metric. And as I say, that the number of confusion metric and all of this value that derive from the confusion metrics will change when we change the value. Okay. And to one ultimate, when I change the threshold to 1, okay? When I change the threshold to 1, I basically have all of the point predicted as 0, isn't it? Right? So you can see that the specificity is 1, right? Because the specificity is that saying that is evaluating the model's capability in capturing the negative point, right? And if we predict all of the point as negative point, then we have 100% specificity, right? And in the other extreme, if I put the threshold to 0, then all of the point will be treated as 1, will be predicted as 1, right? And you will see the sensibility equal to 1, right? Okay, because sensibility is the ability that the model can capture the y equal to 1 point. Okay, so and as I move this threshold from 0 to 1, you will see that in the specificity and sensibility plane, we will have a trace. If we trace this, the point of sensibility and specificity, actually they are a trade-off, as you can see, right? When the threshold is higher and higher, okay, specificity is higher, okay, and the sensibility is lower, okay? And they are actually a trade-off between them, right? Some business they will focus on they will more emphasize specificity, and some business scenario they would emphasize more specificity. And actually, these two things has a threshold, and that can be determined, can be influenced by the number of threshold. Okay. So if we change the threshold, right, adjust the threshold from 0 to 1, so actually we will see a curve in the plane of this specificity and sensibility plane. Okay. And that curve is called ROC curve, okay? And the area under this curve, under this ROC curve, okay, is called AUC, it's called area under curve, okay. See, when we move the threshold, the confusion measure will change, okay, and the sensibility and specificity and also the accuracy will also change, okay. So and when we move the threshold from 0 to 1, we will have a curve, okay. We can draw a curve in this sensibility and specificity plane, and that curve is called ROC curve, okay. And the area under curve is what we want to explain as we will call it AUC, which is the ratio that the model can correctly distinguish the two class, okay. The mathematics is a little bit difficult, but I can actually demonstrate the thing here, right? See, so this AUC, it actually do not, as you can see that, it did not depends on, it's always 0.802, right? Because it already take all of the threshold value into account, okay? So this AUC is actually the capability that the model can distinguish the two class. If your model, this is the predicted probability, so this is simulation, right? So if a model is very good, right? So you can see that the red point and the yellow point, the green point, they are like separated. Okay, if they are separated, then you will see a very high accuracy. AUC, right? So this AUC is kind of like when you take all of this ratio into consideration. Okay, how the model can. The model is used like classify to separate, to distinguish the two class, right? So the most important thing is this value, right? So in the modern data science, basically when we are build model, we would like to choose a model that has a higher AUC, okay? And that means that this model will perform better when we adjust the threshold, okay? And it's already 10 o'clock already, right? So in this first hour, I basically just rehearse the thing that we already learned last week, right? Okay. We talk about the basic idea is like this, right? Where's my point? The basic idea is like this. Okay, you have we have data, right? So after we put the data into model, into the method, into the GRM method, we will build a model, right? Okay, and for this model, we actually can predict the for every point in the testing data, we can predict the probability, right? So we can plot for the 1 point, we plot the histogram, the distribution of probability for y equal to 1. And the green is actually the distribution of predicted probability for y0, right? Okay. And within that, with this distribution probability, if we put on the threshold, we will have the confusion metric, right? The problem is the confusion metric. The number within the confusion metric will change with threshold. Okay, and when we trace the threshold, when we change the value of threshold from 0 to 1, we will have a curve. Okay, and the area under the curve actually can be used to evaluate the capability that this model can distinguish the two different classes. Okay, that is the basic idea, right? Now, this is talking about model accuracy. When we view model in the modern model, as I say, we typically would like to choose a model that has a higher AUC, because in practice we will change the threshold, okay, as we will explain in the next 2 hours. And therefore we would like to choose a model with a higher AUC, which means that no matter where the threshold is, the model has a higher capability in distinguish the two models. Okay, and that is the model accuracy. Okay, and now let's take a break, and we will resume our course at 10 after 10. Okay.
确认一下，就是奖项的部分，就是因为目前这个版本是要英文名字，所以我们想问说，是要用符合他们的那个护照的名称，还是他们自己的随便的英文名字都可以？
问他们一下好。
OK， 好。好，那我们等一下再发文，请他们提供他们要的。
应该是他们用他们学校，他们在学校里面应该有一个。到时候他们毕业证书上面用的那个名字是什么名字？对吧？
符合护照的。
对。
然后另外一个是老师的职称，这样写可以吗？就是这个中山大学的助理。
OK， 这样可以。
谢谢老师。好，那我们这样就可以确认完英文版字就可以用。
好。